This is part B of our in-class liquid-liquid multi-stage extraction problem. If you constrain the flow rate to be 200 moles per hour to each stage, and that is important because we're going to have multiple stages, so we have to specify to each stage, how many stages would you need to achieve this separation? So this is a design problem. We want to calculate the number of stages as the key variable. We are given solvent flow rates for each stage, and we are also given a design specification of 93% pure. So before I show you what the process flow diagram looks like, see if you can draw for yourself what the process flow diagram might look like. So pause and come back. Maybe you had difficulty with that exercise because when we don't know how many stages there are, obviously it's hard to draw the process flow diagram from the outset. What I like to do is just draw one stage and then keep adding on stages as I need them. So fortunately, the design type problem is the easiest class of problem to solve because we don't have to work backwards. We can keep working forwards. So I've put in all the needed information that we had from the problem statement: 500 moles per hour, 40% acetic acid, 60% vinyl acetate, 200 moles per hour of 100% water going to each stage. I can start solving this just stage by stage. So let's go ahead and start with doing stage one. And the first step for any liquid-liquid extraction problem is finding the mix point. And the mixing point for stage one is F plus S is equal to M. F is 500, S is 200, so therefore M is equal to 700. And then we need to find at least one of the compositions, and more if we want to double check our work. So it doesn't matter in this case, all three are about equal. Let's just do water. Water coming in, there is no water in the feed, so 0 times F plus 1 times 200 is equal to X water mixing point 1 times 700. And the composition of water is 200 divided by 700, or 28.5%. So X water mix 1, 0.285. And that's actually the only one number that you need to calculate in order to move on. But I'm going to go ahead and show you the other two just for completeness. If I wanted to do acetic acid, it would be 0.40 times 500 plus 0 times 200. So there is no acetic acid in the solvent, maybe obviously. Is equal to X of acetic acid times mixing point 1 times 700. So 0.4 times 500 is 200. I've got 200 divided by 700 again for my composition of acetic acid at the mix point. And that is also equal to 0.285. Now, vinyl acetate should, of course, be 1 minus 0.285 minus 0.285, and we could calculate it that way. Or we could calculate it the other way. So again, these are not independent equations. I'm just showing you, for the sake of completeness, how you would do it if you wanted to do it. You have options for doing these material balances, and whichever one you want to choose is completely up to you. So this one is 0.6 times 500 divided by 700. That number is 0.429. That is X vinyl acetate of mixing point 1. All right, so I've got 3 coordinates for my mixing point. I could plot that. So I could go to my diagram, ternary diagram, find 28.5% acetic acid, should be about there. 28.5% water, which is about there. And the other 42.9% vinyl acetate, which is about there. And that would give me a mixing point, which is right about here. So this is mixing point 1. Now remember, I told you you didn't have to go through and find 2 of those compositions. You only had to find one of those compositions. So if you only calculated one composition, how would you know where it lies? Well, remember, I can find the mixing line by knowing that I mixed 2 things. So my feed was 40% acetic acid, 60% vinyl acetate. Remember, vinyl acetate lines go that way. Acetic acid lines go that way. And I know that my solvent is pure water, so pure water is over there. So this is solvent of the nth stage. And I could connect those points with a straight line. And my mixing point, again, lies along that line. In fact, it lies along that line 2/7 of the way from feed to S, because I added 200 moles of solvent to 500 moles of feed. That's why the length of this line segment is 2, and the length of the entire line segment is 7, of course, normalized. Again, I don't like to use the lever rule too often, just showing you so you knew how to check your work. All right, I know the mixing point. I can now draw my tie line, and fortunately, I have a tie line that goes directly through, so I'm just going to use that tie line, but red dotted lines are going to be my tie lines. And then I can read the compositions of my raffinate and extract phases directly off the diagram. So for my raffinate, which will be on the left side, on the vinyl acetate side, R1 is there. Let's see, I've got 24% acetic acid, about there. So I'm going to fill these numbers in on the diagram while I'm doing it. 0.24 acetic acid. I'm going to say 66% vinyl acetate. So that looks pretty good, 66% VA, which of course leaves the last 10% by my physical constraint to be water, and I'll quickly double check that, that I do have 10% water, and I do. The extract phase has 32% acetic acid, 0.32 AA. What else do we have? Let's see, 17% vinyl acetate, 0.17 vinyl acetate, which leaves the last 51% to be water. And I'll just quickly double check that. 51% water, we do. 0.51 water. All right, the compositions of the extract and raffinate phases are found. Importantly, the composition of my raffinate is only 67% vinyl acetate, which tells me that one stage is not enough to achieve my desired composition of, remember, 93% vinyl acetate is what we want in the raffinate. So I need to add another stage, but before I can do that, I need to know what the flow rate of R1 is such that I can find the mixing point. So I have to go back and do a material balance to find the composition, to find the flow rates of E1 and R1. Find flows of E1 and R1. Okay, so I've got 3 material balances that I can write. Only 2 of them, remember, I only need 2 of them because there's 2 variables. So I can say that M is equal to E1 plus R1. And I can say that because M is also equal to F plus S. So I know that my mix point was 700. That is equal to E1 plus R1. And then I need one more material balance. I think waters will do here. Water's pretty the simplest, I think. I added only 200 moles of water to it. So I should have 200 moles per water coming in. That is equal to my mole fraction of water in my extract, 51% water times E1 plus 10% water times R1. So 2 equations, 2 unknowns, simple substitution here. Plugging in for R1 into the water balance gives me 200 is 0.51 times E1 plus 0.1 times 700 minus E1. So distribute the 0.1 to give me 70 minus 0.1 E1. 200 equals 0.51 E1. And then I've got some algebra to do. So 130 is equal to 0.41 E1, which gives me that E1 is 317 moles per hour, rounding a little bit. And then R1 is 700 minus 317, so that is 383 moles per hour. So I'd like you to pause the video at this point, and instead of using the water balance to find E1 and R1, go back and verify. Try to use the acetic acid balance and see what numbers you get. And you might be surprised to find that you don't get exactly the same numbers. Remember, that is because the material, just the material balance is a little bit over constrained. And the information should be redundant. But because I'm not perfect at reading these diagrams, and nobody is, you're going to get a little bit of error. So you have to be comfortable with that error. But you should be able to verify that the numbers are at least close to the numbers that I've calculated here. All right, so moving on, let's put these numbers into our diagram. So E1 was 317 moles per hour, and R1 was 383 moles per hour. All right, so we're going to need another stage, so therefore let's go through and do stage 2. We'll do it over here. We need to find the mixing point of stage 2. It is F plus S, but remember F is only the first feed. So actually in stage 2, it's R1 plus S2, where all the S's are the same, but just to make sure we're being clear about what we're counting, S2 is the material balance we need. That is equal to M2. And I should have been careful about my subscripts over in mixing point 1. When we have multiple stages, we want to be careful about naming variables appropriately. So R1 is 383, S2 is 200, therefore M2 is 583. And let's find one composition. Let's use acetic acid again. So let's say acetic acid is 24% acetic acid times 383. There is no acetic acid in the solvent water stream. That is equal to X acetic acid mixing point 2 times 583. Solve that one equation for one unknown. Find that composition of acetic acid at the mixing point 2 is 16%. Now that's all I'm going to do for that one. So I'm going to show you how you would find it a little bit quicker. What am I mixing in stage 2? I'm mixing raffinate 1, which we found in the last stage. So that point is there. We're mixing that with pure solvent. So I'm going to connect the two things that we are mixing. We are connecting R1 to S2, and we know that the acetic acid composition is 16%. So all I have to do is find where acetic acid is 16%, and I must be along this mixing line, maybe something like that. All right, and again, double check if you want. I think it'd be very helpful for you to find what the composition of the other two components are at the mixing point and then compare it to the point that I just wrote in there. So this is mixing point 2. Okay, I don't have a tie line that goes through it, so I can just draw in my own. So I'm going to do that now. This may be something like, oh, I got a little bit too low. I just want something that looks like it doesn't look too out of place and that it belongs. Something like that is pretty good. All right, the intersections with the equilibrium diagram, the equilibrium curve, are again my compositions. So I've got E2 on this side, and I've got R2 on that side. So again, just reading off what the compositions are on the diagram, we'll start with the raffinate. I've got 86% vinyl acetate. If I look there, and I'll try and keep things in the same order, 0.86 vinyl acetate. I've got, we'll say, 11% acetic acid, 0.11 acetic acid, which means that the other 3% must be water. And I'm looking at my water axis down here. I indeed find it's 3%, or close to it at least. And now I'll do my E2. So my E2 composition, I got 20% acetic acid, 0.22 acetic acid. I've got, let's see, 6% vinyl acetate up here, 0.06 vinyl acetate, which leaves the last 74% to be my water. All right, so I am going to pause the video now to erase kind of what I've done so far, kind of declutter it, because I think I'm getting a little bit too cluttered now. If you need to pause the video now and catch up, now would be the time to do so. So I'm going to pause my recording, come back, and erase. All right, that is much better. We are still at 86% vinyl acetate in our raffinate 2 phase. So that means we must need some more stages. And in order to calculate the next stage, I need to find what the flow rates of R2 and E2 are. So see if you can go ahead and do this one with me. Remember, M2 is equal to E2 plus R2. And I know that M2 is 583. And let's do acetic acid again. You could do another component. You won't get the same answer again. You'll get something close. So at the mixing point, I had 16% acetic acid times the flow rate of the mixing point, 583, is equal to 0.2 E2 plus 0.11 R2. Substitute again by saying that R2 is equal to 583 minus E2. So I'll crunch this number. 93.3 is equal to 0.2 E2 plus 0.11, 583 minus E2. Do some more algebra. Find that I've got 29.2 is equal to 0.09 E2, and therefore E2 is 324, and R2 is 583 minus 324. 259 moles per hour. Okay, so I'm going to put these numbers into my process flow diagram. R2 was 259 moles per hour, and E2 was 324 moles per hour. All right, so look at the trends that we've got. We're getting definitely closer to pure vinyl acetate. So we started at 67. Oh, I guess we started at 60. Got to 66 in the first stage, 86 in the second stage. So that kind of suggests that the third stage is going to be all that I need. Notice that the first stage is the most efficient in terms of getting the most acetic acid out. I've got the most acetic acid in my, I got to look at the extract phase, I suppose. So I got 32% acetic acid in the extract, 20% acetic acid in the second stage. As I continue adding more and more stages, I'm going to extract less acetic acid each time, in part because there's less acetic acid to begin with. So those are all the trends that you should be aware of. But let's go through and do stage 3 mixing point. And hopefully this is the third time you've seen it, so you can predict what the calculations will be. The mixing point is R2 plus S3 is equal to M3. And R2 is 259. S3 is again 200. 459 moles per hour. Yep, I'm going to pause and do this calculation. I did not do this. All right, sorry about that. I confused myself for a second, but I'm back on track now. This is the flow rate of the mixing point. I just need one more material balance, so we'll do acetic acid for a third time. The composition of acetic acid in R2 is 11%. Flow rate is 259. That is equal to X acetic acid mix 0.3 times 459. And X acetic acid mix 0.3 is 0.07. And then I also did vinyl acetate just to double check again. But vinyl acetate was 0.86 times 259 equals X vinyl acetate mix 3 times 459. The result is X vinyl acetate mixing 0.3 is 0.49. All right, so I've got two coordinates just to double check. This time I am mixing R2 with S, so that's my third mixing line. 49% vinyl acetate is about there, and thankfully it corresponds with about 6% acetic acid. Now if I draw my tie line such that it looks like it fits in about there, I can look at my extract composition and see that I've got 95% vinyl acetate. And therefore, I would say if the problem only asked me to find how many stages I would need, I would say that I am done with the third stage. 3 stages is the final answer. All right, but if it were to predict what compositions and flow rates I would get out of that third stage, I would then go through with the same algorithm that I've done for the first 2 stages, and I would find what my flow rates and my compositions of my third extract and raffinate phases are. So R3 is again here. I think you get the idea. I don't think I need to go through and show this, although I'm willing to do so if I get feedback that says it would be helpful to go back and do it. But I think you get the idea. And that was how to solve a design type problem. On Friday, we'll talk about the limits of solvent flow rate. So just like there was a minimum solvent flow rate for both distillation and absorption stripping, there's also a minimum flow rate that you have to take into consideration when you're designing a liquid-liquid extraction. All right, thanks for listening.